What if I told you that behind every AI breakthrough, every recommendation you get, every image that gets recognized, there is something absolutely beautiful: mathematics. Today, we are diving into Why Machine Learn by Anil Ananthaswamy. This isn't just another AI book. This is the story of how elegant math became the secret language of artificial intelligence. Meet Anil Ananthaswamy, award-winning science journalist, former staff writer for New Scientist. He mastered something incredible, taking the most complex mathematical concepts and making them crystal clear. His previous books, The Edge of Physics and Through Two Doors at Once, both are acclaimed, both brilliant books. And this book is 448 pages of pure mathematical elegance. Published by Dutton in July 2024. So it's just like a first anniversary of this book, and I wanted to pay tribute for this great book. But what makes it special? It doesn't just explain AI. It reveals the beautiful math that makes AI possible. So, who is the target audience? If you are an AI practitioner wanting deeper mathematical intuition, this is for you. If you are a STEM student exploring machine learning theory, this is for you. If you are a tech professional who wants to understand AI's core mechanism, this is for you. If you are educator teaching computational mathematics, this is definitely for you. Mathematics provides not just the tools, but the very language through which machines learn to see the world. Here is where it gets beautiful. Everything in machine learning starts with vectors and matrices. Look at this. X equals x1, x2, and so on, all the way up to xn. This simple vector, it can represent anything. A person's feature, the pixels in an image, your preferences, your entire digital footprint. Data point exists in multi-dimensional spaces. Spaces so complex that humans can't even visualize them. Here we are just seeing 2 dimensions of this representation. But machines, they navigate these spaces effortlessly. The elegance is stunning. Simple mathematical objects representing incredibly complex real-world phenomena. Linear algebra gives machines superpower. Vector addition and subtraction. That's how machines compare data points, find similarities, spot differences. The dot product that measures similarity between vectors. It's crucial for understanding distances and creating decision boundaries. Matrix transformation. They change vector magnitude, direction, dimensionality. This is the foundation of neural network operations. These operations form elegant mathematical foundation that enables machines to learn from data. Every recommendation, every prediction, every breakthrough, it all starts here. Here is the magic moment. How do machines actually learn? They minimize the difference between their output and desired output. So predicted output and the expected output. Mean squared error. MSE equals 1 over n times the sum of y minus y hat squared. The loss function quantifies how well the model performs. Lower values mean better performance. As the author beautifully puts it, when I wrote the LMS algorithm on the blackboard for the first time, somehow I just knew intuitively that this is a profound thing, and I am sure you will feel the similar way. The goal? Find model parameter that result in the lowest possible loss. This is where mathematics becomes poetry. Gradient descent. The elegant mathematical process that enables machines to learn from data. Theta equals theta minus alpha times the gradient of j theta. Picture a ball rolling down a hill. That's gradient descent. The algorithm iteratively adjusts model parameters to find the minimum of the loss function. Now we can use backpropagation and gradient descent to tweak each of the network's billions of parameters. This elegant mathematical technique, it's what makes modern deep learning possible. It automates optimization through calculus. Let's go back to the beginning, the 1950s. Frank Rosenblatt's Perceptron sparked immense excitement, one of the first learning machines inspired by biological neurons. It could learn, it could adjust weights, it could find linear boundaries separating data points into categories. But then came the XOR problem. In 1969, Minsky and Pippert mathematically proved that single-layer perceptrons can't solve simple non-linear problem like the XOR gate. See the diagram. If you separate the green dots, the red dots falls in the two different part of the region. So this is the XOR problem that Perceptron could not solve. The Perceptron never lived up to the hype. These fundamental limitations led to the first AI winter. Research halted for years. But mathematics found a way. The introduction of hidden layer in neural networks was a mathematical breakthrough that overcame the perceptron's limitations. Multilayer perceptron could learn complex nonlinear relationships in data. The backpropagation algorithm enabled efficient training of propagating error backward through the network to adjust weights. The LMS algorithm is the foundation of backprop, and backprop is the foundation of AI. That's what written in that book. This mathematical innovation solved the XOR problem and laid the foundation for modern deep learning. Deep learning. Neural networks with many hidden layers, vast amount of data, incredible computational power, automatic feature learning. Deep networks learn hierarchical features from raw data. No manual feature engineering needed. Scale and complexity. Modern networks can have billions and nowadays even trillions of parameters. They can model incredibly complex relationships. But here is the beautiful part. Despite their complexity, deep networks still rely on the same elegant mathematical principles. The mathematics hasn't fundamentally changed, but the scale and applications have transformed our world. This book brilliantly reveals the truth. Mathematics is the true foundation of artificial intelligence. From the earliest perceptrons to today's deep learning systems, the elegance of mathematical principles enables machines to learn patterns from data that humans might never discover. Despite increasing complexity, the core mathematical concepts remain consistent. Mathematics provides not just the tools, but the very language through which machines learn to see the world. If you want to understand AI, really to understand AI, you need to understand the mathematics behind it. Why Machines Learn by Anil Ananthaswamy is your guide to this elegant mathematical world. What do you think about this breakdown? What mathematical concept in AI fascinates you? Let me know in the comments below. And if you enjoyed this video, hit the subscribe button. We are just getting started on this journey through the mathematical elegance of artificial intelligence.